Welcome back to the course of Applied Elasticity. In today's lecture, we are going to discuss about the tensor calculus. In 3 previous lectures, we were mostly talking about the tensor algebra, where the initial notations were first introduced and then followed by definition of second order tensor and different tensor algebraic manipulations. Now, we are going to discuss about the calculus related to the tensor quantities. So, first we are going to start with the tensor valued function of a scalar and its derivative. So, let us say t is a second order tensor valued function for a scalar small t, then derivative of capital T with respect to small t is defined to be another second order tensor which is given by this particular expression. ddt of this second order tensor valued function capital T is equals to limit delta t tending to 0, capital T evaluated at time t plus delta t minus capital T evaluated at initial time t divided by delta t. So, this is similar to the formal definition of derivative of any function. Similar to that or following that, the definition of the derivative of a tensor valued function can be given through this particular expression. ddt of second order tensor t is equals to limit delta t tending to 0, difference between the value of t at t plus delta t and at initial t divided by change in t, that is delta t. Now, what are the properties related to this derivative operator for tensor? So, if you are taking derivative ddt for t acting over a, where t is a second order tensor, a is a vector. So, for that, if you are taking the derivative, we will apply the chain rule of differentiation. So, first derivative will be applied on t and keeping a as it is. So, d capital T dt acting over a and plus the second term, in the second term we will apply the derivative on vector a. So, tensor capital T acting over d a dt, this is the first property. Same property is valid if we are having product of two tensors t capital T and capital S. So, d dt of T s is equals to d capital T dt times S plus capital T times d s dt. So, we are taking chain wise differentiation of both the tensors capital T and capital S one after another. And coming to the third property, if the tensor t is multiplied with a scalar valued function of time t, alpha t times t capital T, and then we are taking its time derivative, then there will be two terms. First, the derivative of the scalar valued function d alpha dt followed by tensor capital T plus alpha t scalar function remaining as it is into d dt of the tensor capital T. So, all these chain rule of differentiations are valid for the derivative of tensor valued function as well. Now, we are going to define the gradient of a scalar function, which will be coming across this kind of quantities like this kind of calculus operations such as gradient, curl, divergence, trace, Laplacian in the elasticity problems very often. So, that is why we need to first introduce all these quantities and their formal definition. So, we are starting with phi, which is a scalar field or scalar valued function of x. X vector is the position vector and this scalar valued function can be any scalar function, may be density of the material or electric potential or any other field which is defined within the body, and that is function of location of the point or position vector of any point of the body. So, phi is a function of x vector, this is called a scalar valued function for the position vector x. Now, gradient of the scalar phi is defined to be a vector and that is denoted by this. So, this particular operator is called the gradient operator. So, gradient of phi is a vector and that is defined through this particular equation. Gradient of phi vector dotted with dx vector, small change in the position vector, is equals to phi evaluated at x plus dx minus phi evaluated at initial x. So, through this expression we can define the gradient of any scalar function phi. So, for the rectangular Cartesian coordinate system with base vector E I, we can expand phi x plus dx, this term, in this particular form. So, phi x plus dx is having 3 components: phi of x1 plus dx1, comma x2 plus dx2, comma x3 plus dx3. This is on the left hand side, and this can be expanded in the series solution as phi of x, that is phi x1 comma x2 comma x3 at initial x, the value of scalar function at initial location, plus del phi del x1 into dx1 plus del phi del x2 into dx2 plus del phi del x3 into dx3. 3 first order terms which are contribution due to change in x1 coordinate, change in x2 coordinate, change in x3 coordinate respectively, plus there will be second order term, third order term, and so on, involving dx1 square, dx2 square, dx3 square and all. Now, considering dxi to be small, the higher order terms are neglected, and with that, if we are taking this first term on the right hand side towards left, so it will be phi x plus dx minus phi of x equals to del phi del x1 dx1 plus del phi del x2 dx2 plus del phi del x3 dx3, which using summation convention can be written as del phi del xi into dxi. And by definition of the gradient, this right hand side is equals to grad phi dot dx. So, grad phi vector ith component into dxi, or grad phi vector dot dx vector is equals to phi of x plus dx minus phi of x. So, comparing this grad phi and del phi del xi, we can write that grad of phi ith component is del phi del xi, which is derivative of phi with respect to xi. So, here this comma I, phi comma I, refers to the first derivative of phi, scalar valued function phi, with respect to xi, and in total this gradient vector of phi can be written as phi comma I ei, where comma I refers to derivative with respect to xi and gradient operator is del del xi times ei. This is one operator which can be operated, which can act on any scalar valued function I. Now, similar to the gradient of a scalar, we can also find the gradient of a vector function. Now, how is that defined? Gradient of a scalar was defined to be a vector. Gradient of a vector is defined to be a second order tensor. So, as we are applying gradient operator on any quantity, its order is getting increased by 1. Gradient of scalar was a vector, gradient of a vector is a second order tensor. Now, if we are considering any vector field V, which is function of position vector x, its gradient grad V is defined through this particular transformation. Grad V acting over dx, grad V is a second order tensor that is acting over dx is equals to that vector field V evaluated at x plus dx minus vector field V evaluated at x. Now, in the component form, if you are writing the gradient of V, so gradient of V I j is equals to, by definition of tensor component, this is equals to E I dot grad V acting over E j. Now, V vector is nothing but V1 E1 plus V2 E2 plus V3 E3. V1, V2, V3 are the components of V vector along E1, E2, E3 base vectors or unit vectors, and grad operator is defined as del del xj of Ej. So, using this definition, this particular expression within the bracket, this can be written as del v del xj, and in total this is ei dot del v del xj. If you are taking the dot product of ei unit vector with another vector del v del xj, only the ith component will be remaining. So, thus this would become del v I del xj, that is basically the derivative of the ith component of v with respect to jth component of the position vector. This is written as v I comma j. Comma j means the derivative is with respect to jth component of the position vector, and the subscript before comma, that is I, refers to ith component of the vector field v. So, thus the ij component of second order tensor gradient of v is equals to v I comma j. This is valid for gradient of any vector field. Now, after gradient we are going to the trace operator. Trace of any second order tensor, that we are going to define. Now, second order tensors can be written in terms of its component with the help of dyadic product. Thus, we will first define the trace of dyadic product of two vectors a and b. So, trace of dyadic product a dyadic b is defined to be a scalar, and that is nothing but dot product of a and b. So, a dot b. Trace of a dyadic b is a dot b. Now, coming to any second order tensor T, trace of that tensor T can be written in terms of its components as trace of T I j E I dyadic E j. So, we already know that T tensor in terms of its component can be written as T I j E I dyadic E j. So, that is replaced here. Now, by definition of trace of two dyadic product, this trace of dyadic of E I E j is nothing but E I dot E j, and T I j being a scalar, that would come out of the trace. So, E I dot E j dot product of two unit vectors is basically Kronecker delta delta I j. So, T I j into delta I j, and by using the properties of Kronecker delta, this is nothing but T I I. So, trace of any second order tensor T is equals to T I I, that is basically summation of all the diagonal terms of this second order tensor T. Now, coming to divergence of a vector field. After gradient and trace, now we are going to divergence of a vector field. Now, divergence of any vector field V is defined to be a scalar field. So, you note that when we are taking the gradient of a vector field, that is resulting a tensor, order is increasing by 1, whereas when we are taking the divergence of a vector field, that is resulting a scalar. So, order is reducing by 1 while taking the divergence operator. So, divergence operator, I am writing it here with div, this is the divergence operator. Divergence of any vector field V is defined as trace of the gradient of V. We had already defined trace and gradient. So, divergence of V is equals to trace of gradient of V. Now, gradient of V, this quantity is a second order tensor. If we take rectangular Cartesian coordinate system and try to write the components of this particular right hand side, trace of gradient of V. So, trace of any tensor can be written as T I I, trace of any tensor T is equals to T I I. Here the tensor is grad V. So, trace of grad V is I component of grad V, and we also know that gradient of V, this was defined as V I comma j. So, basically this would result V I comma I. We are taking I and j to be same, as both the indices are same here. Gradient of V is V I comma j, trace of that would result V I comma I. So, divergence of V, divergence of any vector field V is equals to V I comma I. Now, coming to the divergence of a tensor field, this would be resulting a vector. Divergence of a vector is a scalar, divergence of a tensor field T is defined to be a vector, and for any such vector A, this is defined through this transformation law. Divergence of T is a vector dotted with A, another vector, any arbitrary vector A equals to divergence of T transpose A minus trace of T transpose gradient of A. Through this particular transformation, the divergence of our tensor field is defined for any arbitrary vector A. Now, for simplifying this, we will be taking all these terms one by one and then simplify them using the initial notations. So, let us consider left hand side divergence of T dotted with A. So, this is dot product of two vectors, divergence of T is one vector, A is another vector. So, that will be resulting a scalar. So, as left hand side is a scalar, both the terms on the right hand side must result to different scalars as well. So, let us first take the first term, divergence of T transpose A. Here we are assuming a new quantity. So, this T transpose A is assumed to be a new vector B. So, first term is basically becoming divergence of this vector B. Divergence of any vector B is defined to be B I comma I as discussed in just previous slide. So, divergence of B is B I comma I, where B is T transpose A. So, replacing that T transpose A I comma I. Now, T transpose A I is further simplified as T transpose I j A j, and then T transpose I j is equals to T j I, transpose is removed and both the indices I and j are flipped. So, thus this is equals to T j I a j entire thing comma I means the differentiation with respect to x I. So, now if you are applying the chain rule of differentiation, this would result two terms. Once we are differentiating T j I keeping a j constant, which results the first term T j I comma I a j, then we are differentiating second term a j keeping T j I constant, which results the second term T j I a j comma I. So, this is these two terms are coming from the first term of right hand side expression given. Now, coming to the second term, which is trace of T transpose grad of A. This one is defined to be a second order tensor. T transpose is a second order tensor, gradient of A vector is another second order tensor, product of these two second order tensors is defined to be a new tensor A, capital A. Now, trace of any tensor capital A is basically AII. So, this is equals to T transpose gradient of AII. Now, it is product of two tensor, this is first tensor, this is second tensor. With the definition of product of tensors, we can write T transpose IK gradient of AKI by using the product of definition of product of two tensors. T transpose IK can be written as TKI, removing transpose sign and flipping the indices, whereas gradient of AKI by definition of gradient of a vector, this is equals to AK comma I. Thus, this particular term by replacing k with another dummy index j, this is T j I a j comma I. Now, we had simplified both the terms on the right hand side. So, if you combine them in the given fashion, so this term is the first term on the right hand side, divergence of T transpose A minus trace of T transpose gradient of A is this term. Now, if you put this, you can see T j I a j comma I, this term will get cancelled and this will be having a single non-zero term T j I comma I a j. Now, if you go for the left hand side, divergence of T dot A, we can write that as dot product of two vectors divergence of T j times A j and comparing it with the right hand side. So, we are comparing these two, this is right hand side and this is left hand side. A j is common. So, divergence of t, jth component should be same as t j I comma I. So, divergence of any tensor t, ith component of that is defined to be t I m comma n, where m is a dummy index and I is the free index. Here in the previous equation we were having j as the free index, I as the dummy index. Here I have changed the names to be I as the free index and m as the dummy index. So, ith component of divergence of t is t I m comma m. This is divergence of a tensor field, which is basically resulting a vector. Now, coming to curl of a vector field I m comma n, where m is a dummy index and I is the free index. Here in the previous equation we were having j as the free index, I as the dummy index. Here I have changed the names to be I as the free index and m as the dummy index. So, ith component of divergence of t is t I m comma m. This is divergence of a tensor field, which is basically resulting a vector. Now, coming to curl of a vector field. Curl of a vector field is another vector field, and curl of vector v is defined to be twice of the dual vector of the antisymmetric part of gradient of v and denoted as this. So, gradient operator cross product v, this refers to the curl of vector v. It is denoted through this particular form and it is defined as twice of the dual vector T A. So, in one of the previous lecture we had defined the dual vector which is existing for the case of antisymmetric tensors. So, here T A is the dual vector for the antisymmetric part of gradient of V. So, any vector can be written as summation of a symmetric tensor, and any tensor can be written as summation of a symmetric tensor and an antisymmetric tensor. So, gradient of V tensor can be written as summation of a symmetric tensor and an antisymmetric tensor. Here that antisymmetric part is chosen, which can be written as half of grad V minus grad V transpose, and dual vector of this antisymmetric tensor is this T A. Twice of that dual vector defines the curl. So, in the rectangular Cartesian system, curl of V, which is gradient operator cross product V, this is the method by which, the way through which the curl is denoted. This is 2 times T A I, ith component of the antisymmetric dual vector, times E I. E I is the unit vector. Now, if you recall the definition of the dual vector for any antisymmetric tensor capital T, we had defined T1A as minus T32 or T23, where for this particular case T is equals to half of grad V minus transpose of grad V. So, half of grad V minus transpose of grad V is T, and minus T32 was defined as the first dual vector component T1A by definition of dual vector. Similarly, second dual vector component was defined as T13, third one was defined as T21. So, here we are putting those definition of dual vector which we had derived earlier, and the first term T1A becomes half of V3 comma 2 minus V2 comma 3, which with the help of permutation symbol can be written as minus half of E1 jk Vj comma k. Similarly, second and third component can also be written in terms of permutation symbol, and in total if you combine all three, TIA, the ith component of the dual vector of the antisymmetric tensor is equals to minus half of Eijk Vj comma k. Now, definition of curl is equals to double of the dual vector, and with that this half will get cancelled with the 2 existing here, and curl of V, ith component of curl of V vector is minus E I j k V j comma k. Now, we know that E I j k can be written as minus of E I k j by definition of the permutation symbol. So, minus sign can be dropped and we can write this as E I k j V j comma k. Now, flipping the indices j and k, interchanging the names of j and k, this particular thing can be replaced by interchanging j with k and k with j. Thus, curl of V ith component of that becomes E I j k V k comma j, and if we want to use the minus sign, then the first definition can be used, which is minus E I j k V j comma k. So, with this we can define the curl of a vector field, and curl of vector field is another vector field. While using curl operator, there is no change in the order of the system. Now, coming to curl of a tensor field, this is defined to be another second order tensor, so that for any constant vector A, note that constant vector A, not any variable vector. For any constant vector A, the curl of T, another second order tensor dotted A, is equals to curl of A dot T. So, through this particular transformation, the curl of a tensor field is defined. Now, if you consider A dot T, jth component is written as A k T k j, which is equals to T L j A L. Here I am defining or changing the name of the dummy index k with L. Thus, A dot T j will be T L j A L. Now, we are going to take the curl of this particular vector. So, this is a vector quantity. If you are considering right hand side of the given identity, curl of A dot T, this ith component with the help of the curl of a vector definition as discussed in the previous slide, curl of V is minus of E I j k V j comma k, where V is basically this quantity here, A dot T. So, curl of A dot T I component is minus E I j k T L j A L comma k. Now, this comma k means derivative with respect to k component of the position vector x k. Now, we are going to expand this, and if you are taking derivative, it would be minus E I j k A L T L j comma k. Note that here, as A is a constant vector, A L comma k, while taking the time derivative with respect to x k, this term A L comma k should also be coming, T L j times this, using the chain rule of differentiation, but that is taken to be 0 as A is a constant vector. Now, coming to the left hand side of the given equation, curl of T dot A, this is equals to curl of T I L A L. Curl of T is a tensor that is acting over A. Now, comparing both right hand side and left hand side expressions. So, this is the right hand side expression, this is the left hand side expression. If we compare both of them, A L is the common term which will get cancelled, and then curl of T I L is equals to minus E I j k T L j comma k. Thus, the curl of a tensor field can be simplified and written in terms of positive permutation symbol. This minus sign is dropped, E I j k is changed to E I k j with the help of property of the permutation symbol. So, curl of T I L is equals to E I k j T L j comma k, changing the names of the dummy indices k to m and j to n, we can write this as E I M N T L n comma m. So, curl of T I j component is E I M N T j n comma n. Through this, the curl of a tensor field is defined, which is another second order tensor. So, in total in this particular lecture we had discussed about gradient of a scalar and vector function, trace of second order tensor, and this divergence and curl operators which are acting over the vector and tensor field and their corresponding expressions. Thank you.